Oh, hello, friend. Sorry, I didn't see you there. Don't mind me. I was just looking at this blue science liquid. I suppose you're here to talk about the Coriolis effect. Luckily, I happen to have a presentation ready about that very thing. Right? And so, the Coriolis effect is the reason why we see storm systems spinning and why currents in the ocean rotate. And so, our surface currents, our large ones that run throughout the ocean, tend to spin in these big gyres, right? And the reason for that is this Coriolis effect. In order to understand the Coriolis effect, I'm going to ask you to play some imagination time stuff. Right? So imagine that you are Bob, standing on this very happy Earth. Okay? You, as Bob, are great friends with Alessia. Okay? Now, unfortunately, Alessia lives far away from you. She lives way down by the equator, and you live way up near the Arctic. Okay? One fortunate thing, though, is that you guys live in a straight line from one another. Okay? So you happen to live in the same exact time zones. Right? And so when you wake up in the morning at 6:34 a.m. and you feel like FaceTiming Alessia, you can do that because you know that she's awake because it's also 6:34 a.m. All right? And now you had a nice little conversation with her, things are popping off, being friends, and you go on your day and you hit lunch and you're kind of like, oh, that hot dog was really delicious. I want to tell Alessia about that hot dog. And so you look over the clock and it's 1:30, and so you FaceTime Alessia and you're like, yo, Alessia, what time is it there? And she says, it's still 1:30, right? Of course it's still the same time. You guys are in the same time zone, right? And so even though you live vertically very far apart, okay, horizontally on the planet, you're in the same line, right? And so you're moving in equal amount along throughout the day. Right? You're not moving outside of one another's time frame because you're staying in line as the day progresses. Right? And now Giselle and Steve over on the opposite coast are under similar circumstances, and they're experiencing the same thing. The only thing is they don't use FaceTime, right? They like to call on the phone and talk awkwardly. And they like a lot of like awkward silences. So they just sit there on the phone sometimes. Maybe Giselle's, washing some dishes and Steve's watching a football match and they don't really talk, but they're on the phone and the time stays the same because they're vertically in line. All right. Everybody on board? You following me? Right? Time hasn't changed. They don't move outside of each other's time zones. And so you're thinking, well, what does that have to do with storms and currents, Mr. Lavadier? Stop talking your nonsense. Well, let me tell you what. It has everything to do with storms and currents. All right. I want you to go back to being Bob, and you live up in the Arctic. Okay. So this is you. You're Bob now. Okay. And now Alessia was right below you down here on the equator. Okay? If we look at the equator and we compare it to the poles, we notice that that equator is chubby. It's thick, 4 Cs. It's much wider at the equator than it is at the poles. Right? And so the distance that is being covered is much longer at the equator than it is on the poles. But as we established earlier, Bob and Alessia are moving in line. And so even though the middle of the Earth has to travel a further distance than the poles do, they are moving in sync. They're moving at a rotation rate that is 1-to-1, right? And so it's taking the same amount of time to spin around one rotation, but the distance that it is spinning is vastly different, right? And so I have different distance over the same amount of time. And if we put in that context of distance by time, we realize that that's speed, right? And so in that moment, we must recognize that the equator of the Earth is spinning faster than the poles are spinning. The middle of the Earth is going faster than the poles are going, right? And that's a gradation. And so if I'm at the equator, I'm going faster than if I'm at New York City, right? So if I'm standing on the Empire State Building, I'm going slower than if I'm standing an equator place. I don't honestly know much geography. There's some place on the equator, and we'll call it an equator place, and that works. Okay? So even though you're staying in line, because you're rotating at the same rate, the speed that you're moving is different depending on where you are on the Earth. And the closer you are to the equator, the faster you're going. Okay? And you're still probably thinking, like, what does that have to do with storms spinning, Mr. Lavadere? I'm like, all right, we're getting there, all right? Still imagination games. We need more imagination games if we're ever going to understand this. Yeah. So now I want you to imagine you're watching some T-Rexes riding on top of trains. All right. You got these two T-Rexes. They're riding on top of these big bullet trains. Okay. And they're playing catch. Okay. They're throwing an orange between each other on this big bullet train. They're in a vacuum, so the wind doesn't matter. All right. Now, if both T-Rexes are riding these two bullet trains at 20 miles an hour in the same direction, okay, as they stare at each other, okay, it's going to seem that they are staying in the same point of reference, right? And so the train's moving 20 miles an hour, the T-Rex is moving 20 miles an hour, the orange is moving 20 miles an hour in the same direction, right? So they're all staying in line. So as they play catch, since everything is moving in the same direction at the same speed, right, they might as well be standing still. When they throw the orange in a straight line, it's going to go to the next T-Rex in a straight line. He's going to catch it, he's going to throw it, the other one's going to catch it, and he's going to throw it, the other one's going to catch it, back and forth. And they can just play their orange catch game for as long as the bullet trains are riding 20 miles an hour, right? Okay. Now something changes though, all right? Same T-Rexes, same bullet trains, same orange. However, the T-Rex on the top train is now traveling 60 miles an hour as opposed to 20, right? And so as they move along, the T-Rex on the top train is going 60 miles an hour. Therefore, the orange in his hand is going 60 miles an hour, whereas the T-Rex on the bottom train is still going 20 miles an hour. So when the T-Rex on the top train goes to throw the orange to the T-Rex on the bottom train, the orange is now traveling 40 miles an hour faster than the T-Rex on the bottom train. Okay? And so over that course of time, that orange is now going to land in front of the slower train. Right? Can you picture that? You throw it, the orange is going 60 miles an hour, train's only going 20, and so by the time the orange lands, the orange is going to be in front of the slower train, right? By a matter of 40 miles per hour difference. Right? And so that is what's happening on the Earth, right? The wind that is starting down by the equator, okay, and moving away from the equator, okay, is going faster than the land that is under it. Okay? In this storyline, the wind is the 60 mile an hour T-Rex, and the land is the 20 mile an hour T-Rex, okay, as long as we're moving away from the equator. And so even though the wind started going in a straight line, right, it's traveling as fast as the Earth was before, okay, and as it moves over the now slower moving land, okay, it's making ground on it. Right? And so it looks like the wind is spinning. Okay? It looks like it's moving in the forward direction, just like the orange looked like it was moving in front of the train now. Right? Even though the T-Rex threw it straight, it still landed in front of the train. Right? And so even though the wind is going straight from its point of reference, compared to the slower moving Earth underneath it, it's now moving forward in that space. Right? And so you get this arcing motion. Now, as that wind circles and moves back down towards the equator, the Earth is still spinning in the same way, and so our relationship of speed changes. Right? And so now what was faster wind, right, is now moving back down over land that is longer, okay? And so now it seems to be going more slowly. Okay? And so I've changed direction 180 degrees, okay, but I'm starting to go the other direction. And so this spinning will always, from the point of wind, look like it's moving to the right in the northern hemisphere, okay? So from the direction of the wind. So you got to imagine you got your face, you got this wind face, right? And you're going forward and you're turning right, right? Eventually, you turn enough right that what used to be left is now right, right? And so that's how you get it back cyclicking this way. So you're always turning to the right. In the southern hemisphere, it's going the other way. It's always going to the left, but by the same principle. So yeah, T-Rexes on trains is the answer to why the Coriolis effect works. So that's it. Bye.